We will continue with a familiar concept, permutation. If you remember, we defined a permutation as a function. Recall the definition here. A bijection from set A to itself is called a permutation. So this is essentially a new ordering of the elements of set A, and usually, of course, when the number of elements is small, so this is variable, we use Cauchy's two-line notation. In the first row, we just note the elements. In the second row, we put the elements that are mapped to. So here, sigma 1 is 2, sigma 2 is 4, sigma 3 is 5, sigma 4 is 3, and sigma 5 is 1, which means through this bijection, 1 is mapped to 2, 2 is mapped to 4, etc. You get the idea. So a permutation is a bijection from a set to itself. Essentially, what this means is an ordering. And the number of permutations on a set A with cardinality n, where of course n is finite and integer, we are dealing with finite sets now, is n factorial by the product rule. Why? Because essentially you have n tasks here. If you have n elements here, the first element, you need to determine an element to map to this one. Okay? And then after you do that, you have to do the same for the second element. But now you can do this in n ways, but since you have used one of the elements, you cannot use it again because this is a bijection. Okay? It needs to be one-to-one, so you need to pick a new element. Therefore, your alternatives now reduce to n minus 1. And with the third one, it reduces to n minus 2, and so on. With n minus 1, you have two alternatives, and for the final one, you would have just one alternative. And this simply gives you n factorial, the famous result we know, the number of permutations on a set with cardinality n is simply n factorial. An ordered arrangement of R elements from a set A with n elements again is called an R permutation. Now here we are not talking about the permutation function as a function, but it's just an ordering, and now we are using just um, uh, let's say a subset of the elements you have in the original set A. Now this is we call sampling without replacement with order. Okay, so order is important for us uh, because we have to map every element to a distinct element, and sampling without replacement means you cannot recycle elements, you cannot reuse them. Okay, you can use every element once at the most. Okay, so the same approach applies here. You have R subtasks now. This should be R. Selecting the element for the first one, selecting the element for the second one, the third one, etc., up to the rth one. And here you have n alternatives, and the next one it will be n minus 1 because replacement is forbidden. You cannot reuse elements. In the third one it would be n minus 2, etc. And here the final element here will be n minus r plus 1. So this is essentially what we call a falling factorial, n times n minus 1 times n minus 2 times n minus r plus 1. So essentially this is equal to n factorial divided by n minus r factorial. Simple example here, in a race with 100 contestants, the first, second, and the third are awarded medals, like the gold medal, the silver, and the bronze medals. If there are no ties, how many distinct outcomes are going to be in this race? Okay, so this is an R permutation. This is actually the case where n equals 100. So out of 100, I want just 3 elements in an order. So I need order because it makes a difference whether a contestant is the first or the second, because he's going to receive a different type of medal. Okay, so the result is, according to this result here, 100 factorial divided by 97 factorial, which is simply this product.